All right, dears, here we are for lesson 30. Yeah, now it's sad, your very last lesson of the good old pre-calc. We are looking at limits, which is kind of our precursor setup for calculus. The idea of looking at that every function and thing you look at has they don't all have a limit, but there's limitations to the things we do. They approach a certain thing or a certain, I've lost my words. We're going to look at the limits. So you'll see this limit notation down here. It says lim, and then it's going to say as x approaches a number. So it'll use, the arrow, it means approaches. So the way you're going to word this is here you'd say the limit as x approaches 0 of g of x is. So that's saying as x approaches 0, your x value approaches 0, what is the y value of your function? So we look at it, and in order for it to be a valid limit, it has to approach the same number from the negative direction to the positive and from the positive direction to the negative. A lot of words to just kind of say. We're looking at when x is 0 on this one. So here's where x is 0. Okay, remember x-axis, right here's where x is 0. So what is our y value as we approach that? So when we come in from the left to the right, we are approaching our y value approaches 0. They're at an x value of 0. If we come in from the other side, so if we come in from the positive direction, it is also approaching 0. So that allows us to say that the limit as x approaches 0 of g of x is 0. Okay, because right here, my y value at this x value is 0. From both directions, we approach 0. Okay, so if we look at question 2, so we have two different problems here. We have the limit as x approaches negative 2. We're going to take that one first. Okay, so as x approaches negative 2. Our x value of negative 2 is right here. Okay, so this is where our x value is negative 2. We want to see what does it approach, what y value, as we follow our path towards negative 2, what's the y value? So if we start in the negatives and we're headed towards our negative 2x value, we come this way. As we approach right here at negative 2, approaching from the left to the right, my y value right there is negative 2. Okay, so as we approach from the negative, my y value is negative 2. But if we were to approach from the positive side, so if we're coming from left to right, we're up here, but then as we come down and get closer to negative 2, we approach here. Now it's not equal to 0, but it's infinitesimally close. So this open dot means it can be negative 1.999999999999999, which is pretty darn close to 2, so we allow it to be 0. Sorry, my x value is negative 1.999, which is really close to negative 2, so we can count it. So when we go from here, from the positive direction towards the negative, my limit would actually be 0. Since these two limits are not the same, they have to match. So your limit from the positive and from the negative have to match. Since these do not match, we would say the limit here does not exist. If we think through it now, looking at the second part as x approaches negative 1. X value of negative 1 is right here. Okay, so we're going to look for what's my y value as we approach this spot. When we come in from the negative, we come in down here, and then we jump up. When we get to negative 1, at negative 1, my y value right there is 0. So that's approaching from the negative. As we approach from the positive side, we're going to come from the positive, it jumps down to here. As we approach negative 1, the y value there as we approach negative 1 is also 0. Because those match, we can say the limit as x approaches negative 1 of r of x is equal to 0. That's an ugly 0. Hey, by the way, this is called a step function. When it has these different pieces, it's called a step function. So you can see, because there's basically a line on either side of this dot, it's coming into the same point, we're allowed to have a limit there. When we're here coming at negative 2, my lines approach. I wish you could see my hands. I'm doing a great job showing this with my hands, y'all. As we have our lines coming in from down low and up high. They have a different limit at -2, so we say the limit does not exist. Whew. Hopefully you're with me. If not, you guys, when we finish this and you try a couple and kind of read through the lesson, if it's totally whacked crazy and you think you're gonna lose your mind, I can either do a video where you see my cute face, or just look up, go to Khan, or just kind of Google search some YouTube videos just to kind of you just want basic limits. The hard part is it's going to get into the calculus limits. So let me know if this goes crazy. I'm not over testing it. When we do the review, I'll show you basically how the videos, I'm reading text messages a long way, how the questions will go. Okay. We can also find limits based on the graph, just like we did here on these first two. Finding limits given by a graph is a great way. It doesn't always give you a graph, so you have to kind of know what the graph looks like. Absolute value function is this up here. They make V's. That's the negative absolute value. But absolute value works just the same. Since my -2 is inside the bars, when we have a plus or a minus inside the bars, it moves our graph left and right, opposite of what you think. So -2 moves my V to the right 2, like this. So if we're looking at the x value of 1, as x approaches 1, okay, here's my x value of 1. My graph is right here, and I'm going to show you how to figure out its exact point in just a minute. Wow, there we go. So we're saying as we come in from the negative, what is that number? As we come in from the positive, you can see that our limit is going to exist. From left and right, we arrive at a point right here. Okay, to find that y value, go fat dot. As we find this y value, we can just plug our number into our equation. So we're going to say the absolute value of 1 minus 2 would be the absolute value of -1, which is +1. So we'll say our answer would be the limit as x approaches 1 of r of x, the absolute value of x minus 2 equals 1. Whew. Okay, so basically we're just plugging the number in, thinking about the graph to know that our limit does exist. Number 4, we have a rational function. Anything 1 over x is going to make the parent function that looks like this. Okay, they approach the x and y axis. There's asymptotes along the x and y axis. That 2 on the bottom is just affecting our stretch and shrink, but it follows the same basic shape. It hasn't moved left or right anything. It has not gone up and down. Up and down is the only thing that would affect your limit here. But again, we're not going that deep into it, but I need you to know what this parent function looks like to know that if you're dividing by an x, it's going to give you this crazy whooshy graph over here. So let me draw the graph again. Okay, so as x approaches infinity, so as we think about our x going to infinity, we start here, we fall down, but then we pick back up, okay, as we get closer and closer to infinity, infinity goes that way. Okay, as we keep going that way, this graph is going to get closer and closer and closer and closer and closer and closer and closer to 0. It will never actually touch 0, but like we talked about before with that open dot, it's going to become so ridiculously close to 0 that we basically say good enough. So the limit of, as x approaches infinity, of 1 over 2x is going to equal 0. Because as we head towards infinity, my graph gets closer and closer and closer to 0. It doesn't go less than 0 ever. It just gets closer and closer to 0. If, for instance, we looked at this first graph over here, this absolute value function, okay, so now I'm back way over here. If we wanted to know the limit, that's a laser, the limit as x approaches infinity, see, this is why I do 2 circles, x approaches infinity of r of x, looking at this graph here, as we approach infinity, infinity, my x values keep getting greater. My graph continues to go up and up and up and up. The bigger x gets, the bigger my y value gets. So every increasing x value gives me an increasing y value. So the closer to infinity we get, the more infinite my y value gets. It's never going to stop. So we would say that this limit does not exist because it keeps getting bigger. It never stops growing. So if you're approaching the arrows and it's just going off into Neverland, you've got a do not exist. If you've got arrows and you're approaching an asymptote, then you are going to have a limit. It's whatever that asymptote is. Hopefully that made sense. You can rewind and listen to that again if you'd like. Okay, evaluate the following limits by factoring. If you were to do the method where you just plug this in, these are ugly things to graph. If you were to just plug x is 2 into this to kind of get that numerical y value, you would have 2 minus 2 here on the bottom, which means you're dividing by 0, and that's not allowed. Basically, what these graphs do, these rational graphs where we have lots of x's divided by, is they create holes in the graph. This one, oh, it looks, I'll show you, I'll graph it more succinctly in a minute, but it's going to look like this. Okay, and where x is equal to 2, it's actually going to have a hole in the graph. And so that's where we have this. So how to get by that and know what our limit is we're going to factor first, and then we'll plug into our reduced form. So x squared plus 3x minus 10 will factor to x plus 5, x minus 2. That's divided by x minus 2. Right here, the x minus 2's cancel out. This is what I used to teach in Algebra 2. Whenever you cancel those out, it creates a hole in your graph at an x value of 2. We're left with x plus 5. So we're actually going to find the limit as x approaches 2 of x plus 5. In order to find that limit, we're going to plug 2 in. So we're going to say 2 plus 5, that equals 7. So the limit of this graph is 7 as x approaches 2. So as our x value approaches 2, the x value of 2, my y value is approaching 7. From both directions, it approaches a y value of 7. Now, it never actually equals 7, but again, that infinitesimally close, we just call it good enough, and our limit there would be 7. Okay, same thing over here on number 6. If we plug -3 in, it's not going to work well for us, so we're going to say x plus 3, x minus 2. Down here, we've got x plus 3, x minus 1. It creates a hole in our graph at x is equal to -3. Now we're left with x minus 2 over x minus 1. So this graph's, it's not going to graph a line. It's going to graph hold on. My things are the same. I'm trying to remember rules. It's not graphing a line. Let's just put it that way. We want to find the limit. So we're going to plug in. Point being, you don't have to know what the graph looks like to be able to solve these problems. Once we've got our factors reduced, your factors are always going to match whatever your limit you're trying to find is on these because they're designing it purposely that way. We're going to plug in that -3. So -3 minus 2 divided by -3 minus 1. -3 minus 2 is -5. -3 minus 1 is -4. Since they're both negative, our limit would be 5/4. Okay? So the limit as x approaches -3 of x squared stuff over x squared stuff is equal to 5/4. Okay, I'm going to start a new video for the back page.